So what's up guys, this is the Round Bottom Flask, and for today's video, we will be talking about intermolecular forces. So what are these intermolecular forces? So they are more accurately known as non-covalent interactions, and these are set of forces that are exerted between molecules or between atoms in a molecule. Now the term intermolecular forces of attraction, or IMFA for short, is more constricting because it's more limited rather kay kabaluta nga non-covalent interactions by its definition is not only limited between molecules but it also exists within the molecule itself. Now, by its name, intermolecular forces of attraction only concerns between different two or more molecules. Now, if it exists on a single molecule, those forces does not become intermolecular, but rather it now becomes intramolecular. But then again, they are still these two forces, the intermolecular, intramolecular forces, are still under the more general term non-covalent interactions. And another thing is that when you non-covalent interactions does not only cover forces of attraction but also covers forces of repulsion. Now these forces, both attraction and repulsion, are what holds the physical state of pure substances and the shape of your larger molecules. Now these balance between non-covalent attraction and repulsion makes matter appear what it is. So, case in point, water is liquid at room temperature because of these non-covalent interactions between water molecules. These non-covalent interactions also give that distinct double helical shape of your DNA. So there are several types of non-covalent interactions, namely dipole-dipole interactions, your London dispersion forces, your hydrogen bonding, and your ion dipole interactions. Now, the first three that I have mentioned earlier are under a larger umbrella or a larger classification of non-covalent interactions, which are what we call as van der Waals forces. So let's discuss first what is a dipole-dipole interaction. Now, a dipole-dipole interaction exists within a polar molecule. So what do you mean when we say a polar molecule? Now, a polar molecule is a molecule that has a partial positive and a partial negative, that bears a partial positive and a partial negative part, okay? Now, this partial positive and partial negative end of a molecule is born out from the huge differences of electronegativity between atoms in a bond. So I will discuss that in detail in a different video. Now these partial charges in a molecule, these partial charges that we see here in a molecule is the one that exerts electrostatic attraction with each other. So if we have this molecule here, this has a partial negative charge and this one has a partial positive charge, they will exert electrostatic attraction with each other to give you this complex network of dipole-dipole interactions wherein there is a combination of both attractive and repulsive forces. So remember that opposite charges attract and same charges repel each other. So that is also applicable to your partial charges. So a partial negative bond, a partial negative charge will be attracted to a partial positive charge and vice versa, while a partial negative charge will repel another a fellow partial negative charge. Same goes with a partial positive charge. So this dipole-dipole interactions is characteristic with your water molecule. I will go back to our previous slide. Oops. If you can see here, oxygen, since it has a larger electronegativity, will bear a partial negative charge, while the one with a smaller electronegativity, which is hydrogen, is the one that will bear a partial positive charge. Now, the oxygen end of the water molecule will be attracted to the hydrogen end of the water molecule, and this creates a network of the dipole-dipole interactions, which holds the water together, making it liquid in room temperature. Next that I will discuss is the London dispersion forces. Now, unlike dipole-dipole interactions, which only exist in polar molecules, London dispersion forces exist in all molecules, may it be polar or nonpolar. So to explain London dispersion forces, it is actually a bit complicated. So to make it short, this is due to an induced dipole formed in a molecule. So let's have an illustration here. So here, let's have this, I think this is helium. Let's have an helium atom, for example. Now we know that electrons constantly move around within their respective orbitals in an atom. Now, if we can freeze every moment that an electron moves, there will be one moment that both electrons of a helium atom will be located on one side of the molecule. So, case in point here in frame 3. Now, in this case here, if you notice, since both electrons of the helium atom is on one side of the molecule of the atom rather, this side will become partially negative, while on this side where there are no electrons, it will become partially positive. So thus, at this frame or at this fleeting moment, there is a temporary dipole. Now this temporary dipole will form a cascade with the neighboring atoms, such that since you have a partially negative charge here and partial positive charge here, ang tupad nga atoms ng helium, ang iyang electrons mas mapalapit man sa partial positive charge sang tupad yaman nga helium. Thus, it will be a cascade creating a temporary dipole in the rest of the bulk of the atoms, and thus this instantaneous dipole that is created will exert electrostatic attraction or repulsion with each other. So it's like dipole-dipole interactions, but only for a brief moment. Now, since this is concerned with the movement of this temporary dipole is due to the movement of electrons, it is more obvious that the greater the area or the volume that your electrons can move around, the greater the chance for a temporary dipole to be created. Thus, the stronger will be the London dispersion forces. So this is observed with our noble gases here. Now, if you notice, from helium to xenon, their boiling point increases as the atomic radius of the noble gases increases. So the increase in the boiling point also indicates an increase in the intermolecular forces of attraction. So how does the boiling point become an indicator of the strength of your non-covalent interactions in an atom, in a pure substance in general? This is because that, remember that boiling point is the point wherein a substance in the more condensed liquid phase will be broken away to a more free or to a less condensed gas phase. So what happens here is the higher the boiling point, the higher the heat that you will need to break the intermolecular forces holding the atoms or the molecules or the units together in the liquid state para mangin gas sila. So, kung mas taas ang boiling point, that means mas kusog ang ila intermolecular forces of attraction. Okay? And this summarizes what I have just said earlier. Okay? Lastly, and also, the strength of your London dispersion forces is also dependent on not only the surface area, but also the effective surface area of contact. So this will also concern the shape of a molecule. So let's have two molecules here that has the same chemical formula. Now, in this molecule here, namely N-pentane, if you notice, iyang effective surface area is mas lapad because it is almost rectangular in shape, okay? And while neopentane is almost spherical in shape, and we know that a rectangle or a rectangular prism has a greater surface area than a sphere. So obviously, mas dako ni siya So obviously, mas kusog ni ang iya nga London dispersion forces. So what does the surface area of contact, why does the effective surface area of contact matter? Remember that in order for London dispersion forces to occur, the instantaneous dipole of one molecule should effectively induce the instantaneous dipole to other molecules in the bulk, and that instantaneous dipole can only be induced from one molecule to the other if they have effective surface area of if not in close contact, at least a close proximity with each other para may ara sa London dispersion force, para may ma-form nga instantaneous dipole. So, kung gamay ang surface area for instantaneous dipole, mas mabudlayan ang molecule nga mag-induce dipole halin sa iya pakadto sa tupad ya. I hope you get my point, okay? So, thus, the more prismatic or the closer it is as a rectangular prism, not as it is to a rectangular prism, the greater the surface area of contact for London dispersion forces, thus the stronger the London dispersion forces. Lastly, we have hydrogen bonding. So hydrogen bonding is a special type of dipole-dipole interactions. It's basically a dipole-dipole interaction, but this is only applicable when your hydrogen between molecules that has a hydrogen atom bonded to a more electronegative atom. So for example, your oxygen and your halogens, your oxygen, nitrogen, and your halogens. So again, an example of a hydrogen bonding is your water. So when water solidifies, it becomes ice, right? Now this unique H bonding network gives this characteristic crystal structure of your ice, and that also gives that ice that's characteristic, and that what also makes ice what they call this, less dense than liquid water. And this hydrogen bonding also exists in biomolecules, specifically in your cellulose. If you can see, there is extensive intramolecular and intermolecular hydrogen bonding between in your cellulose, which makes cellulose one of the strongest and hardest biomaterials known to man. Okay, so that also makes the wood very, very hard. Lastly, we have ion dipole interactions. And this is only observed in homogeneous solutions, particularly when your solute is an ionic salt. So this is observed when ions are dissolved in a polar solvent. So obviously, what happens is the partially charged ends of your polar solvent will be attracted to your ions, obviously on opposite charges. So let's have the dissolution of your sodium chloride. So what happens here is that the water molecules in your ion will form some sort of a cage around your ions. So in this case, in your sodium cation, it will attract the oxygen, specifically the partially negative portion of your oxygen ion, of your water molecule, while your chloride and ion will attract the partially positive end of your water molecule. So we have discussed all of these intermolecular forces. However, how do they compare in terms of strength? So obviously, the strongest will be the ion dipole because it is between a full-blown charge and a positive charge. Next is we have your hydrogen bonding. Next is your regular dipole-dipole interactions. And the weakest is the London dispersion forces because it is only formed by an instantaneous dipole, which immediately dissipates after a brief moment. So that's the end of my video for intermolecular forces. Here are my references again. If you think this video is interesting, please subscribe. Don't forget to like this video and please subscribe to my YouTube channel for more interesting videos regarding chemistry. So that's it, guys. This is again the round bottom flask. See you